Somewhere in the darkness above your head, there is a galaxy so large that if you replaced the Milky Way with it, its outer edges would reach past every star you have ever named, past every constellation your ancestors drew in the dirt, past the nearest 400 neighboring galaxies, and it still would not be done. We think we understand large. We have stood at the edge of oceans and felt small. We have looked up at mountains and understood, somewhere beneath language, what insignificance feels like. But the human mind was built for a world of faces and distances you can walk. It was never designed for what lives out there, past the comfortable boundary where numbers stop behaving like numbers and start behaving like something closer to myth. Our galaxy, the Milky Way, the only home our species has ever known, contains 400 billion stars and spans 100,000 light-years from edge to edge. That alone should be enough to stop you cold. And yet, what you are about to encounter is the story of what happens when even that scale becomes a rounding error. It is the story of IC 1101, a galaxy over 1 billion light-years away that rewrites every intuition you have about size, about age, about what a single object in the cosmos is even allowed to become. It is the story of galaxies that grow not with stars, but with violence, twin jets of plasma stretching across 20 million light-years of space, fired from a single point of darkness at the center of everything. And it is, quietly, a story about us. About why we keep measuring things that refuse to be measured. About what it means to point a telescope at the void and refuse to look away. The place to begin is home, because you cannot understand how lost you are until you first understand exactly where you started. The galaxy we call home, and why it's not enough. There is a moment, if you have ever stood far enough from city lights, when the sky stops being a backdrop and becomes something else entirely. The stars stop being decorations, they start being distance. And somewhere in that shift, somewhere between looking up and truly seeing, the ground beneath your feet begins to feel a little less solid, a little less like the center of anything. That feeling is the beginning of cosmology. We begin where we live, not on Earth, not in the solar system, but in the structure that contains both of those things and hundreds of billions more like them. We begin in the Milky Way. Say those words slowly enough, and they almost lose their meaning. The Milky Way. We have called it that for so long, named it after the pale smear of light it paints across a clear night sky, that the name has become comfortable, familiar, domestic even. But familiarity is one of the most effective disguises that strangeness has ever worn. Because the Milky Way, this thing we have named after milk, this cosmic address we carry without thinking about it, is so vast that the human mind cannot honestly hold it. We can describe it, we can map it, measure it, model it with equations that fill pages. But hold it, feel it, in the way you feel the size of a room you are standing in. That is something else entirely. That may not be possible at all. Let us try anyway. The Milky Way is a barred spiral galaxy, seen from above, from some vantage point that no human being has ever occupied or likely ever will. It would look like a slow, luminous pinwheel, a bright, dense core, thickening at the center into what astronomers call a bar, an elongated region of older stars running through the middle like a spine. From that bar, spiral arms curve outward in long, graceful arcs, trailing gas and dust and nurseries of young stars. The whole structure rotates, slowly, over timescales that dwarf anything we call history. Our solar system, riding on one of those spiral arms, a relatively modest stretch called the Orion Arm, or sometimes the Orion Spur, completes one full orbit around the galactic center roughly every 225 million years. The last time we were in this same position, the first dinosaurs were only just beginning to appear on Earth. From edge to edge, the Milky Way spans approximately 100,000 light-years. That is the number that appears in textbooks, the figure astronomers have settled on as a reasonable estimate of the galaxy's diameter. But it is worth pausing on what a light-year actually means before we go further, because the phrase gets used so casually in conversations about space that it begins to sound like a normal unit of measurement. It is not. A light-year is the distance that light travels in a single year. Light, moving at just under 300,000 kilometers every second. In 1 second, light can travel around the Earth 7.5 times. In 8 minutes, it crosses the distance between the Sun and our planet. In just over 4 years, it crosses the distance to our nearest stellar neighbor, Proxima Centauri, which is itself so far away that every spacecraft humanity has ever launched would take tens of thousands of years to reach it. 1 light-year is roughly 9.5 trillion kilometers, and the Milky Way is 100,000 of those. If you were to travel at the speed of light, the absolute speed limit of the physical universe, a velocity so extreme that no object with mass has ever come close to achieving it, a speed that makes our fastest rockets look like they are standing still. If you were to travel at that speed in a perfectly straight line from one edge of the Milky Way to the other, the journey would take 100,000 years. 100,000 years. Modern human civilization, in its broadest sense, is somewhere between 10,000 and 15,000 years old. Writing has existed for perhaps 5,000 years. The Roman Empire, which still shapes the laws and languages of half the world, lasted for less than 1,500 years. The entire span of recorded history, every war and empire and discovery and work of art that human beings have ever documented, fits comfortably into the first few percent of the time it would take to cross our own galaxy at the speed of light. And that crossing would not touch another galaxy. It would not leave the neighborhood. It would simply bring you from one edge of the Milky Way to the other, through a single, ordinary, mid-sized spiral galaxy among hundreds of billions in the observable universe. The thickness of the Milky Way adds another dimension to this. The galaxy is not a flat disk so much as a lens-shaped structure, thicker at the center and thinning toward the edges, with a vertical depth of roughly 1,000 light-years through most of its disk. But surrounding the visible disk is something less obvious and harder to see: the stellar halo. A vast, roughly spherical cloud of older stars, ancient globular clusters, and dark matter that extends out to perhaps 300,000 light-years or more from the galactic center. The halo is sparse, ghostly compared to the glittering density of the disk, but it is enormous. It is the invisible scaffolding that holds the more visible galaxy together, and we are only beginning to understand how far it truly reaches. At the center of all of this, buried deep in the constellation we call Sagittarius, sits one of the most extreme objects known to exist: Sagittarius A star, a supermassive black hole with a mass roughly 4 million times that of our Sun. 4 million solar masses compressed into a region smaller than the distance between the Earth and the Sun. We cannot see it directly, not with our eyes, not with ordinary light. But in 2022, a global network of radio telescopes coordinated as a single Earth-sized instrument produced something extraordinary: an actual image of the shadow of Sagittarius A star, the silhouette of its event horizon against a blurred ring of glowing gas. For the first time, the monster at the heart of our galaxy had a face, and yet, for all its power, Sagittarius A star is relatively quiet as supermassive black holes go. It is not actively devouring enormous amounts of material right now. It is not blasting jets of energy across the galaxy. It sits at the center like a sleeping thing, patient, ancient, holding the spiral structure of the Milky Way loosely in the invisible grip of its gravity. Scattered throughout the disk and halo are the Milky Way's stars. Roughly 400 billion of them, by current estimates, though that number carries real uncertainty. Counting the stars in your own galaxy is, absurdly, one of the harder tasks in astronomy, precisely because you are inside it. Mapping the Milky Way is a bit like trying to draw a detailed floor plan of a building while standing in the middle of one of its rooms with no windows and the lights only partially on. We piece the picture together from what we can measure: the motions of stars, the distribution of gas and dust, the positions of star-forming regions, the data returned by missions like Gaia, the European Space Agency's extraordinary star-mapping spacecraft that has been cataloguing the positions and movements of nearly 2 billion stars with unprecedented precision. 400 billion stars, each of them a sun, many of them orbited by planets, some of those planets almost certainly sitting at the right distance from their star, with the right chemistry for liquid water to exist. We do not know how many. We may never know, but the numbers involved make the possibility of life elsewhere, of intelligence elsewhere, feel not like a wild hope, but like a quiet statistical expectation. This is our home. This is the galaxy we were born into, not through any choice or design, but simply because it happened to be here, at this place in the universe, at this moment in cosmic time. And the Milky Way does not travel alone. Gravity is sociable. Galaxies, like stars, tend to cluster together, drawn by mutual attraction across distances that would otherwise seem impossibly isolating. The Milky Way belongs to a collection of galaxies known as the Local Group, a gravitationally bound family of roughly 54 known members, though that number continues to be revised upward as new dwarf galaxies are discovered lurking at the edges of the group. The Local Group spans something in the range of 10 million light-years, a number so much larger than the Milky Way itself that it requires a moment to absorb. The two largest members of the Local Group are the Milky Way and the Andromeda Galaxy, a spiral galaxy similar in many ways to our own, located approximately 2.5 million light-years away. Andromeda is the most distant object visible to the naked eye under dark skies, a faint, smudged oval of light that looks unremarkable until you remember that you are looking at 1 trillion stars, that the light entering your eye left that galaxy before modern humans existed as a species. Andromeda and the Milky Way are approaching each other. In approximately 4.5 billion years, the two galaxies will collide, their stars mostly passing through each other like two swarms of bees merging, their central black holes eventually spiraling together into something far larger than either. The galaxy that results, sometimes called Milkomeda by astronomers with a taste for the informal, will be a very different structure than either of its parents. An elliptical galaxy, likely rounder and less organized, the spiral arms long since scrambled by the violence of the merger. But that is billions of years from now. For the moment, the Local Group holds together in relative stability. Beyond Andromeda, the next most prominent member is the Triangulum Galaxy, smaller than both spirals, sitting roughly 3 million light-years away. Then come the satellites, the large and small Magellanic Clouds, irregular dwarf galaxies that orbit the Milky Way and are visible from the southern hemisphere as bright, detached patches of the Milky Way itself, though they are in fact separate galaxies in their own right. Around Andromeda orbit its own satellites, small galaxies caught in its gravitational embrace. And scattered throughout the Local Group, barely detectable without dedicated sky surveys, are dozens of ultra-faint dwarf galaxies, some of them containing only a few million stars, ghostly structures that are more dark matter than anything else. For a long time, for most of human history, the local group would have been everything. Not because people knew about it, but because it represents a natural ceiling for intuitive comprehension. 10 million light-years, 54 galaxies, hundreds of trillions of stars. It feels, if you let yourself sit with it, complete, final, like the full accounting. And here is where something important happens, something that this entire story depends on. Humans have always defined enormity by the largest thing they know. The mountain that fills the horizon was once the boundary of the conceivable world. The ocean that took months to cross was once the edge of the known. The solar system, once we understood it, seemed for a while like the appropriate frame for thinking about space. Then came the understanding that our sun was just one star among many. Then came the understanding that those many stars formed a galaxy. Then the understanding that the galaxy was one of many. Each revelation did not simply add information, it restructured the imagination, it moved the ceiling. The Milky Way has been our ceiling for a long time. Even people who know intellectually that there are hundreds of billions of galaxies in the observable universe still feel the pull of the Milky Way as the upper limit of lived cosmic scale. It is so large that it functions, emotionally, as a synonym for everything. When we stare up at that smear of light on a clear night, something in us says, "This is it. This is the full extent of things." It is not. There are galaxies in this universe that make the Milky Way look like a footnote, structures so enormous that comparing them to our home galaxy is less like comparing a mountain to a hill and more like comparing a mountain to a grain of sand. There are galaxies that have consumed other galaxies the way a wave consumes a stone. There are galaxies whose light has been traveling toward us since the universe was young. Structures that assembled themselves slowly over billions of years through a process of accumulation and merger and gravitational collapse that we are only now beginning to understand. One of them sits at the center of a galaxy cluster more than 1 billion light-years from Earth. It is not famous the way that black holes and nebulae are famous. It does not have the popular recognition of Andromeda or the cultural weight of the Milky Way. But among astronomers, it occupies a singular place, a benchmark for understanding just how large a single galaxy can become. Its name is IC 1101, and it is, by most measures, the largest galaxy that has ever been found. What that means, exactly what it means, and why the question of size turns out to be more complicated and more fascinating than it first appears, is where we are going next. So we've stood at the edge of the Milky Way, at least in our minds, and felt the vertigo of it. 100,000 light-years of spinning stars and ancient dust, a structure so vast that light itself, the fastest thing in the known universe, would need longer than our entire civilization has existed just to cross it. And we called that incomprehensible. We called that beyond the reach of human intuition. We meant it. But here is the problem with the universe. It doesn't stop. It doesn't pause to let you catch your breath, doesn't wait for you to feel comfortable with one order of magnitude before offering you something larger. It simply keeps going. And somewhere out there, about 1 billion light-years from where you're sitting right now, there is something that makes the Milky Way look like a dust mote drifting through a cathedral. Its name is IC 1101, and it is the largest known galaxy in the observable universe. The story of its discovery is, like so many things in astronomy, a story of catalogs and patience. IC stands for Index Catalog, a supplement to the new General Catalogue of Deep Sky Objects assembled in the late 19th century. These catalogues were the product of thousands of hours of careful observation, astronomers pressing their eyes to eyepieces and sketching what they saw in the dark: smudges, spirals, ellipses, things that were clearly not stars but whose nature was, for much of that era, deeply uncertain. IC 1101 was logged as a faint, diffuse object, unremarkable in the way that brief catalogue entries are unremarkable. A number, a position, a description that would have fit a dozen other objects. There was no sense in that initial noting of the thing that it was anything other than one more piece of the vast celestial inventory being painstakingly assembled by the astronomers of that age. It would take the tools of modern astrophysics, the mathematics of redshift, the sensitivity of space-based telescopes, and decades of follow-up observation to begin to understand what that faint smudge actually was. IC 1101 lives in the constellation Serpens, the Serpent, one of the 88 officially recognized constellations. It sits over 1,040,000,000 light-years away from Earth. Just hold that for a moment. The light you would be receiving from IC 1101 if you were staring at it through a telescope tonight left that galaxy over 1 billion years ago. When that light began its journey, multicellular life on Earth was still a relatively recent experiment. The first land plants were hundreds of millions of years in the future. The dinosaurs hadn't happened yet. The light now reaching your eye is an ancient message, a fossil of photons, carrying an image of a galaxy as it existed in a universe that bore only a passing resemblance to the one we live in now. And what does that image show us? This is where things get quietly unsettling. IC 1101, seen through a telescope, is not dramatic. It doesn't blaze. It doesn't spiral in great glittering arcs. It doesn't look the way things that are supposed to be extraordinary are expected to look. It appears as a diffuse, softly glowing ellipse, brightest at the center and fading toward its edges with a kind of slow, gentle dimming that gives it the quality of mist more than fire. It is, in the language of classification, an elliptical galaxy. No spiral arms, no pinwheel structure, no dramatic star-forming regions lit up in vivid blues and pinks. Just a smooth, featureless, almost foggy glow, ancient light from ancient stars, stretched across space so vast that even a galaxy the size of IC 1101 looks modest from over 1 billion light-years away. That modesty is an illusion. It is one of the most profound illusions in all of observational astronomy. Let's begin with the numbers, because there is no way to approach IC 1101 honestly without them, and yet the numbers themselves are almost treacherous. The moment you hear them, your brain will try to file them alongside other large numbers it has encountered, to normalize them, to make them manageable. Resist that impulse, because these numbers do not belong in the category of things that are merely very large. They belong in a different category entirely. IC 1101 contains approximately 100 trillion stars. 100 trillion. The Milky Way, our vast and incomprehensible home, contains somewhere between 200 billion and 400 billion stars depending on how you count. 100 trillion is at minimum 250 times that number, probably more. If every single star in the Milky Way were a single grain of sand, you would need roughly the contents of a substantial beach to represent IC 1101, and not a small beach. Stars are burning nuclear furnaces the size of entire planets or larger, and IC 1101 contains so many of them that our entire galaxy's stellar population is essentially a rounding error. But it's the size that truly strains the mind. The diameter of IC 1101's luminous core, the region where stars are concentrated enough to be readily detected, is approximately 550,000 light-years. Remember that the Milky Way spans about 100,000 light-years edge to edge. IC 1101's core alone is roughly 5.5 times wider than our entire galaxy. 5.5 Milky Ways, laid end to end, would still not span the bright, concentrated central region of this one object. And then there is the halo. Elliptical galaxies like IC 1101 are surrounded by vast, diffuse regions of stars that have been scattered and redistributed over billions of years of gravitational interaction. These stellar halos are tenuous things. The stars within them are spread so thin that the halo looks practically empty compared to a galactic core, but they are real, and they are enormous. The stellar halo of IC 1101 extends outward to an estimated 4 million light-years from its center. 4 million light-years. To put that in terms we can actually ground ourselves in, the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years from Earth. If you picked up IC 1101 and placed it exactly where the Milky Way sits, its outer stellar halo would reach past Andromeda. It would swallow Andromeda. It would extend beyond the entire local group, the collection of more than 50 galaxies that includes the Milky Way, Andromeda, the Triangulum Galaxy, and dozens of smaller satellites, and drift out into what we currently think of as intergalactic space. This is why some descriptions of IC 1101 invoke the idea of it swallowing the observable universe's neighborhood wholesale. The claim is not hyperbole, it is just geometry. The tennis ball comparison exists because our minds need something to hold. If the Milky Way, all 100,000 light-years of it, were somehow compressed to the size of a tennis ball, roughly 6.5 centimeters across, then IC 1101's central luminous region would be roughly the size of a large watermelon, maybe 30 or 40 centimeters in diameter. That sounds manageable almost. But IC 1101's full halo, on that same scale, would extend to something like 26 meters across. That's not a watermelon anymore, that's a building. That's the length of a large house or a small aircraft. You could hold the Milky Way in your palm, and IC 1101 would envelope the entire room you're standing in and extend through the walls in every direction. Even that analogy collapses under scrutiny, though, because it asks you to think of galaxies as solid objects with edges when they are nothing of the sort. A galaxy is not a ball, it is not a disk. It is a gravitationally bound collection of stars, separated by distances that are themselves astronomical, embedded in gas and dark matter, with regions that blend and blur and fade rather than cut cleanly against the backdrop of space. The tennis ball captures size ratios, but it obliterates the reality of what a galaxy actually is, which is mostly nothing, punctuated by fire, held together by invisible mass, drifting through a universe that is itself mostly nothing. IC 1101 is not a big ball. It is an incomprehensibly vast volume of space that happens to contain more matter than almost anything else we've ever found. To understand why IC 1101 exists at all, why it grew to this particular extraordinary scale, you need to understand something about its position in the universe. IC 1101 is what astronomers call a brightest cluster galaxy, or BCG. This is a specific designation for a specific kind of object, the single most luminous, most massive galaxy sitting at or very near the gravitational center of a large galaxy cluster. IC 1101 holds this position within a structure called Abell 2029, a massive galaxy cluster containing hundreds of individual galaxies, all orbiting within a shared gravitational well filled with hot gas and dark matter. Abell 2029 is itself a substantial structure, one of the brighter and better studied clusters in the sky, and IC 1101 reigns at its center like a sovereign at the middle of a court. That position is not a coincidence, it is a destiny written in gravity. When galaxy clusters form and evolve, their constituent galaxies don't simply orbit peacefully forever, they interact, they merge. Smaller galaxies fall inward, drawn by the cluster's gravity, and the galaxy sitting at the very center of the gravitational well is ideally positioned to intercept and absorb those falling objects. Over billions of years, the BCG at the heart of a cluster like Abell 2029 grows by cannibalism, by drawing in galaxies that wander too close and incorporating their stars, their gas, their dark matter halos into its own ever-expanding bulk. IC 1101 is the product of that process taken to an extreme, a galaxy that has spent billions of years at the gravitational crossroads of a major cluster, collecting the debris of collisions and absorptions, growing ever more vast and ever more massive with each encounter. This feeding history is written in its appearance. Those smooth, featureless elliptical galaxies, and IC 1101 is among the most extreme examples, are understood to be the aftermath of multiple major mergers. When two spiral galaxies collide, the ordered structures that make spirals beautiful, the arms, the disk, the rotating patterns, are scrambled. Stars are flung outward. Gas clouds collide and collapse into bursts of new star formation that exhaust quickly. What remains, after the violence settles over hundreds of millions of years, is an elliptical, smooth, pressure-supported rather than rotation-supported, its stars moving in every direction rather than all spinning in a common plane. IC 1101 has been through this process not once but many, many times. Every smooth curve of its glow is a record of swallowed galaxies, of mergers so numerous and so ancient that their individual stories have been erased, smoothed over, absorbed into the featureless whole. And this brings us to perhaps the most striking thing about IC 1101, the fact that lingers after the numbers have been stated and the comparisons have been drawn. IC 1101 is old. Not just old in the way that ancient things are old, but cosmically, geologically, profoundly old. Its stars are predominantly old stars, red and orange and cool, burning through their remaining fuel at a slow and steady pace. The reddish color of the galaxy, visible even in telescope images, is not the red of hot young stars or glowing nebulae. It is the red of age, of a stellar population that formed billions of years ago in the early universe, when star formation was violent and rapid and consumed enormous amounts of raw material in relatively short astronomical timescales. IC 1101 blazed once. It burned with a ferocity that we can only infer from what it has become, and then it quieted. There is very little active star formation in IC 1101 today. The gas reservoirs that feed new stars have been largely depleted or heated to temperatures where they can no longer collapse into stellar nurseries. What remains is what was built long ago, slowly cooling and aging across the billions of years since. IC 1101 is not a living, dynamic, evolving structure in the way that younger galaxies are. It is something closer to a monument, a record. The largest single structure of the type we call a galaxy that the universe, in approximately 13.8 billion years of existence, has managed to produce, and it is, in a meaningful sense, finished, not dead, but done growing in the dramatic ways it once grew. What additions come now are small, slow, almost imperceptible on any time scale that a human civilization could observe. There is an emotional texture to that reality that goes beyond the purely scientific. We tend, when we think about grand and extraordinary things, to imagine them in their moment of maximum drama. a mountain in eruption rather than in stillness, a star in its supernova rather than in its quiet main sequence lifetime. But IC 1101, the largest known galaxy, the most extreme example of galactic scale that we have found in the observable universe, is not in a moment of drama. It is in a moment of slow, cold, monumental quiet. It drifts at the center of its cluster, warming slightly as smaller galaxies still occasionally spiral toward it, but mostly simply existing, enormous and ancient and featureless, a vast dark ellipse glowing softly in a universe that is itself slowly cooling. It is the kind of thing that, once you know it's there, changes the way you think about scale. The Milky Way felt vast, and it is. But IC 1101 recontextualizes it the way that seeing a mountain range for the first time recontextualizes every hill you've ever climbed. It doesn't diminish the Milky Way. It simply reveals that the Milky Way exists within a universe that permits objects of an entirely different order of magnitude to exist alongside it. That the cosmos contains multitudes, and that the multitudes go larger than we instinctively expect. But IC 1101 raises a question that is, in some ways, more interesting than the galaxy itself. How does something like this happen? How does the universe, starting from the nearly uniform hot plasma of the early cosmos, produce a structure that spans 4 million light-years and contains 100 trillion stars? What physical processes, operating over what timescales, with what ingredients, lead to an object so extreme? Because IC 1101 is not an anomaly in the sense of being physically impossible. The laws of gravity, of gas dynamics, of cosmic expansion allowed it, created it. And understanding how it grew is really a question about how the universe builds things at all. How structure emerges from chaos, how small becomes large, how a billion years of collisions and mergers and gravitational attraction can compound into something that, from a billion light-years away, still glows with the quiet authority of the most massive galaxy we have ever found. That is the story we need to tell next, the story of how giants are born. So we've established the shape of the problem. IC 1101 sits out there, more than a billion light-years away, a vast elliptical smear of ancient light that dwarfs the Milky Way by almost every measure we can apply to it. We've named it, we've gestured at its scale. But naming something extraordinary is not the same as understanding it. And if IC 1101 is going to mean anything more than a number too large to feel, we need to ask the deeper question, not what it is, but how. How does a galaxy grow to that size? What machinery, operating over billions of years, could possibly produce something so enormous? The answer turns out to be one of the most elegant and violent stories in all of science. Start at the very beginning. Not the beginning of IC 1101, but the beginning of everything. In the first fractions of a second after the Big Bang, the universe was extraordinarily uniform. If you could have stood outside it, which you couldn't because there was no outside, and looked in, you would have seen a nearly perfect, searing hot soup of matter and energy expanding in every direction simultaneously. Nearly perfect. That word matters, because buried within that almost uniformity were tiny wrinkles. Quantum fluctuations, variations in density so small they existed at scales far beneath anything we could ever build an instrument to detect directly. In an ordinary world, these ripples would have meant nothing. But gravity is patient, and gravity does not forget. Over millions of years, those microscopic density variations began to matter. Regions that were ever so slightly denser than their surroundings had slightly stronger gravitational pull. That pull drew in nearby matter, which made those regions denser still, which made the gravity stronger, which drew in more matter. a feedback loop running silently across the entire observable universe simultaneously. The technical term for this is gravitational collapse. The poetic term, if you're inclined toward poetry, is the universe learning to clump. But ordinary matter, the protons and neutrons and electrons that make up stars and planets and you, wasn't the only thing doing the clumping. Most of the matter in the universe is something else entirely, something we can't see, can't touch, can't sample or catalogue or photograph. We call it dark matter, and while we don't know what it actually is at the particle level, we know what it does with extraordinary precision. It clusters, it clumps, it forms enormous invisible structures we call dark matter halos, vast gravitational scaffoldings that reach across millions of light years. And it was these halos that provided the skeleton around which the first visible structures in the universe would grow. Think of it this way. Imagine you're trying to build a city, but you don't have a ground to build on. You're trying to pile bricks in open air, and they keep drifting apart. Now give that air an invisible but solid framework, a lattice of interconnected struts that catch and hold the bricks wherever two struts cross. Suddenly the bricks have somewhere to go. They fall toward the intersections, accumulate, and something starts to take shape. Dark matter halos were exactly this, the invisible architecture that gave ordinary matter a place to collect. Inside these halos, gas began to fall inward. As it fell, it compressed. As it compressed, it heated. And as the universe expanded and cooled around it, some of that gas began to radiate away its heat and cool below a critical threshold. When it cooled enough, it collapsed further, and in the densest pockets, something ignited. The first stars. The universe was perhaps 100 million years old, a cosmic infant, when the first points of light flickered on in the darkness. And around those stars, and between them, the first proto-galaxies began to take shape. Not the elegant spirals and ovals we classify today, but small, irregular, turbulent clumps of gas and young stars tumbling through the early universe like embers shaken loose from a fire. Here is where the story gets personal for IC 1101. Because those first small clumps were not the end of the process, they were the raw material, the model of galaxy formation that cosmologists have spent decades assembling, and that the evidence overwhelmingly supports, is called the hierarchical model. The word hierarchy is key. Small structures form first, and then those small structures combine into larger ones, which combine into still larger ones, over and over across billions of years, building the cosmos from the bottom up rather than the top down. In this picture, every large galaxy you've ever seen is the descendant of an almost unimaginable number of smaller ancestors. The Milky Way almost certainly consumed dozens of smaller galaxies to become what it is today. We can still read the evidence of some of those ancient mergers in streams of stars that arc through our own galactic halo, the stellar remnants of satellite galaxies that wandered too close and were torn apart. Astronomy, at its most intimate, is forensics, and the crime scene is the sky itself. Now scale that process up, way up, and run it for several billion years more. That is IC 1101. The current understanding is that IC 1101 has been merging with other galaxies, absorbing them, cannibalizing them, adding their mass to its own for the better part of the universe's entire history, not occasionally, repeatedly, systematically. Every galaxy that wandered within gravitational reach became part of IC 1101 over and over and over again. There is no dramatic moment of creation here, no single event we could point to and say, this is when IC 1101 became IC 1101. It grew continuously through accumulation, the way a glacier grows by absorbing every snowflake that falls upon it, one after another, for an eternity. But growth doesn't happen in isolation. Context matters enormously. And IC 1101 has the best possible context. It sits at the center of a galaxy cluster called Abell 2029. Galaxy clusters are the largest gravitationally bound structures in the observable universe. They are enormous concentrations of hundreds or even thousands of galaxies, all held together by gravity and by vast clouds of superheated gas that fills the space between the galaxies themselves. Abell 2029 is among the more massive clusters we know of, a behemoth even by cluster standards, and at its very center, occupying the position of maximum gravitational advantage, sits IC 1101. Being the central galaxy in a cluster like Abell 2029 is not a passive position, it is an active advantage. The gravitational well at the center of a cluster is the deepest point in the local cosmic landscape. Anything falling into the cluster, individual galaxies, streams of gas, smaller clusters merging from the surrounding cosmic web, tends to fall toward the center, which means it tends to fall toward IC 1101. The galaxy doesn't have to chase its food comes to it. This process has a name in astronomy. It's called cannibalism, and the term is unusually apartment. When a smaller galaxy falls into the gravitational domain of a massive central galaxy like IC 1101, tidal forces, the difference in gravitational pull between one side of the smaller galaxy and the other, begin to stretch and distort the infalling galaxy. Stars get pulled out of their original orbits. The structure of the smaller galaxy begins to dissolve. Over hundreds of millions of years, the stars and gas that once belonged to the smaller galaxy are redistributed into the halo of the larger one. The smaller galaxy doesn't just stop existing, it becomes part of something else. It is consumed, and Abell 2029 has been feeding IC 1101 for a very long time. There is another ingredient to this story, one that is in some ways the most counterintuitive. The supermassive black hole at IC 1101's center. We believe IC 1101 harbors a black hole with a mass somewhere in the range of several billion times the mass of our Sun. By comparison, the supermassive black hole at the center of the Milky Way, Sagittarius A star, masses roughly 4 million solar masses. IC 1101's central black hole is therefore at least 1,000 times more massive, perhaps more. And this black hole is not merely a passenger at the heart of the galaxy. It is one of the architects of the galaxy's structure. Here is the paradox. You might expect that a black hole of this magnitude would simply pull in everything around it, feeding endlessly, growing without limit, drawing the entire galaxy into itself. But that's not what happens. When a supermassive black hole is actively feeding, drawing in gas and matter from its surroundings, it releases staggering amounts of energy, not from within the black hole itself, but from the superheated material just outside it, spiraling inward in an accretion disk. That energy radiates outward in the form of light, heat, and enormously powerful jets of matter that can extend hundreds of thousands of light years into the surrounding space. We call this an active galactic nucleus, and in its most dramatic incarnations, it outshines the entire rest of the galaxy combined. Those jets and that radiation do something critical. They heat the gas in the surrounding environment. They push it outward. They prevent it from cooling and collapsing into new stars. In other words, the very process by which the black hole feeds can simultaneously shut off the fuel supply that would allow the galaxy to keep forming new stars. It is a governor on a runaway engine, a built-in limit that prevents any single galaxy from growing so massive and so luminous that it destabilizes the entire cluster around it. Astronomers call this feedback. It is one of the most important self-regulating mechanisms in the entire cosmos. For IC 1101, this feedback almost certainly played a decisive role in shaping what the galaxy looks like today. The galaxy is old. Its stars are old, reddish, cool, long-lived, because the era of active star formation ended long ago. The gas that might have continued building new generations of stars was heated and dispersed by the activity of the central black hole. What remains is a vast, aging stellar population, still luminous, still enormous, but no longer growing through birth, only through consumption. And this brings us to perhaps the most telling feature of IC 1101's appearance. It is an elliptical galaxy. Ellipticals don't get the romantic treatment that spirals do. When people picture a galaxy, they usually picture something like the Milky Way or Andromeda, a flat, rotating disk with winding spiral arms, rich with gas and dust, glittering with young blue stars. Ellipticals look nothing like this. They are smooth, rounded, three-dimensional blobs of stars, more like enormous globular clusters than the flat pinwheels we tend to romanticize. And for a long time, this difference in appearance was something of a puzzle. Why would some galaxies be flat spirals and others be rounded ellipticals? The answer turns out to be violence. When two spiral galaxies of comparable size collide, and galaxy collisions happen far more often than you might expect, simply because galaxies are far larger relative to the distances between them than almost any other class of object, the collision disrupts everything. The stars themselves rarely actually strike one another. The distances between individual stars are too large for that. But the gravitational interaction between the two galaxies is catastrophic. The spiral arms that once swept through each galaxy in orderly rotation are flung into chaos. Stars that were following circular orbits in a disk are hurled into new trajectories that carry them above, below, and through the plane of the original galaxy. The gas clouds that once fed star formation are compressed and shocked into violent bursts of new star-making, followed by rapid depletion. And after billions of years of this gravitational chaos, what emerges is not two spirals and not some ragged hybrid, but something smoother and rounder. The stellar orbits have been randomized. The disk is gone. What's left is an elliptical. IC 1101 has lived through this process not once, not twice, but an almost incalculable number of times. Every major merger it has undergone, and there have been many, has contributed stars and mass to its growing halo, while erasing any trace of ordered spiral structure those infalling galaxies once possessed. The result is an object almost perfectly described by the physics of accumulated violence, smooth, featureless, enormous, and ancient. A graveyard of former galaxies, so thoroughly mixed together that no individual lineage can be traced. And yet this is not a pessimistic story. Or at least, it doesn't have to be. What the elliptical form of IC 1101 tells us is that we are looking at something that has arrived. Not in the sense of having finished, the universe isn't done yet, but in the sense of having traveled further along the arc of galactic evolution than almost anything else we can observe. IC 1101 is what galaxies become after enough time, enough mergers, enough gravitational processing. It is a preview, an extreme example of a trajectory that our own Milky Way is also traveling, if far more slowly and modestly. In about 4 billion years, the Milky Way and the Andromeda galaxy will collide. Astronomers have modeled this collision with considerable precision, and the result, on a timescale of several more billion years after first contact, will be a new merged galaxy, already informally nicknamed Milky Way. It will almost certainly be an elliptical. Its spiral arms will be gone. Its star-forming gas will be largely depleted. It will be larger than either of its parents, smoother, older, a small step along the path that IC 1101 has traveled so much further. This is the context in which IC 1101's existence makes sense. Not as an aberration, not as a mystery requiring some exceptional explanation, but as the logical endpoint of processes that are running everywhere in the universe simultaneously. Gravity amplifying tiny fluctuations, gas cooling into stars, galaxies assembling from smaller pieces, mergers randomizing structure, black holes both feeding and regulating, and cluster environments providing the richest possible hunting grounds for the most dominant galaxies at their centers. IC 1101 had every advantage: a deep cluster potential well, billions of years of cosmic time, and the gravitational authority that comes with being the largest fish in an already enormous pond. The result is the galaxy we described in the previous chapter, that soft, diffuse, billion-light-year-old elliptical that appears almost featureless in our telescopes, precisely because it has processed so much through itself that nothing distinct remains. But here is the thing: we've been treating largest as though it were a simple designation, as though there were a ruler somewhere we could hold up to IC 1101 and every other galaxy and simply read off the numbers. Largest by what measure, though? By diameter? By mass? By the number of stars it contains? By the extent of its diffuse outer halo? The answers don't always agree, and as it turns out, depending on how you choose to define the word largest, IC 1101 may have competition it didn't even know existed. The question of which galaxy truly deserves the title of the universe's biggest is, it turns out, far more philosophically complicated than it first appears, and the answer has been quietly rewritten more than once in the last few years. Defining largest, why the question is harder than it sounds, so now we understand how these giants come to be. We have traced the arc from quantum whispers in the infant universe all the way to the merging of galaxies across cosmic time, the slow accumulation of matter guided by dark matter scaffolding, the cannibalizing of smaller neighbors, the feeding on cosmic filaments stretching across the void. We understand the process, but here is where the story becomes unexpectedly complicated, because understanding how IC 1101 grew is in some ways the easier problem. The harder problem, the one that astronomers argue about in journals and at conferences, the one that keeps careful scientists up at night, is something far more fundamental. What does it actually mean to say that something is the largest galaxy in the universe? That question sounds as though it should have a clean answer. You measure it, you compare the measurements, you declare a winner. But science, especially science at the frontier of human knowledge, is rarely that polite, and the question of galactic size turns out to be one of the most instructive examples in all of astronomy of how the act of measurement is never innocent. Every measurement carries assumptions, every instrument has limits, every number we assign to something as vast and diffuse as a galaxy is, in a very real sense, a negotiation between the cosmos and the tools we bring to understand it. Start with something that seems obvious. A galaxy has a size. It has an edge. Somewhere it ends and intergalactic space begins. Except that is not quite how galaxies work. Unlike a planet which has a surface, or a star which has a photosphere where its light essentially stops, a galaxy does not have a boundary in any crisp physical sense. What a galaxy has instead is a gradient. Stars near the core are densely packed, blazing, gravitationally crowded together. Moving outward from that center, the density of stars decreases and keeps decreasing and keeps decreasing, until eventually the stars are spread so thin that the distinction between inside the galaxy and outside the galaxy becomes almost philosophical. Imagine standing in a fog. Near the center of the fog, you cannot see your hand in front of your face. Walk outward, and the fog begins to thin. After a while, you can see 10 feet ahead of you, then 20, then 100. At some point, the air around you is mostly clear, but there are still wisps, still faint tendrils of moisture drifting past. At exactly what point did you leave the fog? There is no line on the ground. There is no moment when the fog simply stops. And yet astronomers, when they publish a measurement of a galaxy's size, have to draw that line somewhere. Where they draw it depends on their tools, their methods, and their definitions. One common approach is to measure what is called the effective radius, the radius within which half the galaxy's total light is contained. Another approach looks for the point where the brightness of the galaxy falls below a certain threshold against the darkness of the surrounding sky. Yet another approach tries to trace the outermost detectable stars, the so-called stellar halo, which can extend far beyond what casual observation would suggest. Each of these methods is legitimate. Each of them is internally consistent, and each of them will give you a different number for the same galaxy. For IC 1101, this matters enormously. Depending on which method you apply and how sensitive your instruments are, you can arrive at figures that differ not by a small margin, but by a factor of several. Some measurements of IC 1101's diameter cluster around roughly 6 million light-years, already a staggering figure that dwarfs the Milky Way's 100,000 light-years by a factor of 60. But other estimates, accounting for the galaxy's full dark matter halo and its most extended stellar material, push that figure considerably further. The core, the dense luminous heart of the galaxy, is itself enormous. But the full extent of what gravitationally belongs to IC 1101, the complete structure including its diffuse outer envelope, is something even that 6 million light-year figure may understate. This brings us to one of the most important distinctions in the study of giant galaxies, and it is one that does not get nearly enough attention outside of professional astronomy. When we talk about a galaxy's size, we might be talking about several completely different things. We might mean its diameter, the straight line distance from one detectable edge to another. We might mean its stellar mass, the total amount of matter locked up in its stars. We might mean its total luminosity, how much light it produces across all wavelengths. Or we might mean the extent of its dark matter halo, the enormous invisible cocoon of gravitational influence that surrounds every large galaxy and extends to distances that ordinary observation cannot directly see. IC 1101 ranks differently on each of these scales. In terms of stellar mass, it is extraordinary. Some estimates place its stellar mass at roughly 100 times that of the Milky Way, making it one of the most massive objects of its kind in the observable universe. In terms of luminosity, it is similarly dominant, outshining the Milky Way by a factor that is almost absurd to contemplate. But it is in the domain of halo extent, the full gravitational reach of the structure, that IC 1101's claim to supremacy becomes most dramatic and simultaneously most contested. The halo of IC 1101 is so vast, so diffuse, so extended, that it blurs the boundary between what we call a galaxy and what we call something else entirely. And that brings us to a problem that is not just about measurement, it is about definition. IC 1101 does not sit alone in space. It sits at the gravitational center of a galaxy cluster called Abell 2029. A galaxy cluster is exactly what it sounds like, a collection of dozens to thousands of galaxies bound together by gravity, embedded in a cloud of superheated gas, all sitting within a shared dark matter halo that can be far larger than any of the individual galaxies within it. The question that astronomers genuinely disagree about is this: where does IC 1101 end and the cluster begin? IC 1101 is a type of galaxy called a brightest cluster galaxy, or BCG. These objects form at the centers of galaxy clusters over billions of years, cannibalizing their neighbors and drawing in streams of diffuse stellar material from all directions. Over time, they accumulate vast envelopes of stars that were never really part of any individual galaxy, stars that were stripped from other galaxies through tidal interactions, stars that drifted in from the general stellar population of the cluster itself. This diffuse material, spread thinly across enormous volumes of space, is called intracluster light, and it occupies an uncomfortable middle ground. Is it part of IC 1101? Is it part of the cluster? Does the distinction even have a clean answer? If you are generous in what you include in the boundary of IC 1101, if you draw your line far out into the diffuse envelope of stellar material surrounding the luminous core, you get a galaxy of almost inconceivable extent. If you are more conservative, if you insist on drawing the boundary where the density of stars clearly belonging to the galaxy drops off sharply, you get something smaller, still enormous by any ordinary standard, but smaller. The number you report depends on the philosophy of your boundary as much as it depends on the physics of the object. This is not a flaw in our science, it is a feature of reality. Nature does not organize itself into neat categories for our convenience. The universe did not consult astronomers when it decided how matter should be distributed across cosmic scales. The gradient between a galaxy and its surrounding environment is a genuine physical fact, not merely a gap in our knowledge. And grappling with that fact is part of what it means to do science seriously. One of the places where this problem becomes most acute is in the detection of ultra-faint outer halos. Even setting aside the philosophical question of where IC 1101 ends, there is the practical question of whether our instruments are sensitive enough to detect all of what is there. Elliptical galaxies like IC 1101 have what astronomers call a low surface brightness at their edges. This means that the amount of light per unit of area on the sky is extremely small, not because there are no stars, but because the stars are spread across such vast distances that their combined glow barely rises above the natural background glow of the sky itself. For most of the 20th century, this was an almost insurmountable obstacle. Photographic plates and early digital detectors were simply not sensitive enough to reveal these ultra-faint structures. Astronomers would observe a giant elliptical galaxy and record what they could detect, a reasonably sharp-looking oval of light, not realizing that what they were seeing was only the brightest inner fraction of a much larger, much dimmer structure extending far beyond the edge of their images. It was like standing in a dark room with a weak flashlight, assuming that whatever the beam did not illuminate simply did not exist. Beginning in the 1990s and accelerating through the first decades of the 21st century, a new generation of deep imaging surveys began to transform our understanding of these galaxies. By using extraordinarily long exposures, by carefully subtracting the contribution of background light sources, by combining multiple images to reduce noise, astronomers began to reveal what had always been there but never seen. Galaxy after galaxy turned out to have extended stellar envelopes reaching far beyond their previously catalogued boundaries. Objects that had been measured at one size for decades were suddenly revealed to be significantly larger. The maps that astronomy textbooks had confidently published were, in some meaningful sense, wrong. Not wrong about the bright central regions, but incomplete about the full extent of these structures in the dim outer volumes. For IC 1101 specifically, and for brightest cluster galaxies more generally, this kind of deep imaging has been continuously revising the picture upward in terms of scale. Each improvement in detector sensitivity, each refinement in the techniques used to remove contaminating light, has tended to reveal more galaxy further out. There is something humbling in this. We have been looking at the largest galaxy in the known universe for over a century, and we are still, in some sense, discovering how large it actually is. But here is why all of this matters beyond mere record-keeping. Here is why the question of which galaxy is largest and how we define that size is not just trivia for astronomers who like superlatives. The size distribution of galaxies, the statistical map of how many galaxies exist at each size, is one of the most powerful tests of our fundamental theories about how the universe works. Our best cosmological models, the ones built on the framework of dark matter and dark energy and the standard model of cosmic structure formation, make specific predictions about how galaxies should be distributed across a range of sizes. They predict how common small dwarf galaxies should be, how common medium-sized spirals like the Milky Way should be, and how rare truly enormous galaxies like IC 1101 should be. These predictions arise from the underlying physics of how dark matter halos collapse and merge over time, governed by the geometry and content of the universe as a whole. When astronomers find an object sitting at the extreme tail of this distribution, an object like IC 1101, far larger than typical galaxies, far larger than most models would comfortably predict, it does not just raise eyebrows. It potentially challenges the models themselves. Either the models need refinement, or our understanding of how we measure galactic size needs refinement, or both. Every extreme object is an opportunity to test whether our theories can accommodate reality, or whether reality is telling us something new. This is particularly important for our understanding of dark matter. The halos of large galaxies are not directly visible. We infer their size and mass through gravitational effects, through the way they deflect and distort light, through the dynamics of the stars and gas moving within them. If IC 1101's halo is as extraordinarily extended as some measurements suggest, then the dark matter structure sustaining it must be correspondingly vast. And that has implications for how dark matter clusters, how it behaves on the largest scales, and whether our models of its properties are accurate. Dark energy enters the picture too, in a more indirect but still profound way. The universe's large-scale structure, the cosmic web of filaments and voids and cluster nodes, is shaped by the competition between gravity pulling matter together and dark energy pushing space apart. The largest gravitationally bound structures that can exist are, in a sense, a direct readout of where that competition stands. A galaxy cluster, with an exceptionally massive brightest cluster galaxy at its heart, is a probe of the gravitational landscape on scales that few other observations can reach. Measuring it carefully is not an academic exercise. It is empirical pressure on the deepest theories we have about the nature of reality. And so when astronomers debate whether IC 1101 is 6 million light-years across, or somewhat larger, when they argue about whether the intracluster light should be counted as part of the galaxy, when they push the limits of their detectors to trace the faintest outer wisps of stellar material at the galaxy's edge, they are not splitting hairs over a number. They are probing the universe's architecture at its extremes, testing models that describe the largest story we know how to tell. There is something philosophically vertiginous about this. We began by admiring IC 1101 from a distance, struck by its sheer scale. And then we moved closer, scientifically speaking, and discovered that the closer you look at where the galaxy ends, the less certain the answer becomes. The edge of the largest galaxy in the known universe is not a wall or a surface or even a precise location. It is a question that dissolves into smaller and smaller uncertainties the harder you push on it. This does not diminish IC 1101. If anything, it deepens it. The galaxy is not merely a record in a catalogue. It is a living argument about what galaxies are, about how we know what we know, about the relationship between our instruments and the reality they probe. It is an object at the boundary not just of observed scale, but of observed understanding. And if the definition of largest is this complicated for IC 1101, a galaxy we have been studying for decades with the most powerful telescopes ever built, imagine what happens when an entirely new object arrives on the scene. An object so extreme, so thoroughly outside the expected range of what should exist, that astronomers initially question whether their instruments have failed them. An object that does not just push the record slightly further, but shatters it so completely that the whole conversation about galactic size has to be restarted from scratch. That object has a name, and what it suggests about the universe we live in is more unsettling and more wonderful than almost anything IC 1101 has told us. So we've established that measuring a galaxy, even deciding where it ends, is less like drawing a line and more like arguing about where the ocean becomes the shore. The boundary shifts depending on where you stand, what instruments you use, what definition you're willing to defend. And for IC 1101, that ambiguity stretches the galaxy's possible diameter from the already staggering to the nearly incomprehensible. But here is where the story takes a turn. Because there are objects in this universe that have settled the question of size in a completely different way, not through stellar mass, not through the gradual accumulation of ancient stars spread across millions of light years, but through something more violent, more focused, and in some ways more difficult to believe even after you've seen the data. They are called giant radio galaxies. And to understand why they matter, you first have to understand what they are and how they differ from everything we've discussed so far. When astronomers talk about IC 1101, they are talking about a galaxy shaped by time. Billions of years of mergers, absorptions, gravitational gathering, the mass piles up, the stellar halo grows, the galaxy becomes enormous the way a city becomes enormous, through centuries of expansion outward from a dense, ancient core. It is a slow process, measured in epochs. Giant radio galaxies grow differently. They are not primarily defined by the number of stars they contain or by the width of their stellar disk. They are defined by what their central black holes are doing right now, or rather, what those black holes were doing hundreds of millions of years ago, since the light telling us about them has been traveling ever since. At the heart of many large elliptical galaxies sits a supermassive black hole. This is not unusual. Most galaxies of significant size harbor one. But occasionally, under conditions that astronomers are still working to fully understand, these black holes enter a feeding frenzy. Material spirals inward. The region immediately surrounding the black hole, called the accretion disk, heats to temperatures that dwarf anything found inside a star. And in the chaos of that process, something remarkable happens. Twin beams of plasma, ionized gas threaded through with magnetic fields, are launched outward along the black hole's rotational axis, not slowly, not gently, at very nearly the speed of light. These are relativistic jets, and in the largest cases they do not stop. They punch through the center of their host galaxy, through the surrounding halo of gas and dark matter, out into intergalactic space, and then they keep going for millions of light years, sometimes tens of millions, carrying energy across distances so vast that the host galaxy itself, with all its billions of stars, becomes a tiny footnote at the center of the structure, like a period at the midpoint of a sentence that stretches across an entire room. The question of how these jets remain coherent across such distances is one that genuinely puzzles physicists. You might expect a beam of plasma, launched from a single point, to spread and dissipate over millions of light years. Intergalactic space is not truly empty. It contains a thin, hot plasma of its own, and the interaction between the jet and this medium should, in principle, slow and scatter it. And yet, in giant radio galaxies, the jets hold together. They remain collimated, meaning they stay narrow and focused, rather than splaying outward, across distances that seem to defy reason. The best current explanation involves magnetic fields. The plasma within the jet is not simply matter moving fast, it is matter threaded through with powerful magnetic fields that act as an internal scaffold, keeping the beam from dispersing. The jet essentially carries its own structural integrity with it, maintained by the same electromagnetic forces that launched it in the first place. Additionally, the environment the jet travels through matters enormously. In the voids between galaxies, where the intergalactic medium is thinner and cooler, jets encounter less resistance. They can travel farther before losing energy to friction with their surroundings. This is one reason that the largest giant radio galaxies tend to live in particular cosmic neighborhoods, a point that will become important very shortly. When these jets finally do slow and spread, they inflate enormous lobes of radio-emitting plasma. These lobes are what radio telescopes detect. Vast bubbles of energetic material that glow at radio wavelengths invisible to the human eye, but unmistakable to the right instruments. The entire structure, the host galaxy, the jets, the terminal lobes, is what astronomers call a radio galaxy, and the giants among them are objects that should, by any reasonable intuition, not exist at the scale they do. In 2022, a team of astronomers using LOFAR, the low-frequency array, a network of radio telescopes spread across Europe and linked together to function as a single enormous instrument, announced the discovery of one such object. They named it Alcyonius, after the giant of Greek mythology who was the son of the sky god Uranus. The name was fitting. What they had found was, at the time of its announcement, the largest known galaxy in the universe, measured by physical extent. Alcyonius is located roughly 5 billion light-years away. Its host galaxy is, by the standards of elliptical galaxies, surprisingly ordinary. It is large, but not exceptional. Its central black hole, while certainly massive, is not the most massive ever catalogued. And yet, extending outward from this relatively unremarkable core, its jets stretch for an almost impossible distance, approximately 16.3 million light-years from tip to tip. Let that number breathe for a moment. The Milky Way, as we established, spans roughly 100,000 light-years across. Alcyonius, from one jet lobe to the other, measures more than 160 Milky Ways laid end to end. If you could somehow transplant our entire galaxy, all 400 billion stars, all the dark matter halo surrounding it, everything, into the jet of Alcyonius, the Milky Way would be swallowed without notice. You could repeat that process more than 80 times in each direction from the center and still not reach the end. What makes Alcyonius particularly interesting to astronomers is precisely this mismatch between cause and effect. The host galaxy's mass is not extraordinary, the black hole's mass is not extraordinary, and yet the jets are record-breaking. This suggests that the size of these jets is not simply a function of how powerful the black hole is. The environment into which the jets are propagating matters deeply. The density of surrounding gas, the structure of nearby cosmic filaments, the specific thermal conditions of the intergalactic medium in that particular region of the universe. Alcyoneus appears to live in an unusually underdense environment, where its jets have encountered minimal resistance and have been able to extend themselves across timescales of hundreds of millions of years without losing coherence. In other words, Alcyoneus is not just a story about an extreme black hole. It is a story about an extreme conversation between a black hole and its cosmic neighborhood. The universe shaped it as much as its central engine did. Astronomers celebrated the discovery, papers were written. Alcyoneus entered the record books, and then, 2 years later, the record was broken. In 2024, a research team announced the detection of a radio galaxy they named Porphyrion, another giant of Greek mythology, and by any measure the more apt name, because what they had found did not merely surpass Alcyoneus. It redefined what astronomers thought was possible for a single gravitational object to accomplish in a single human lifetime of cosmic activity. Porphyrion's jets span approximately 23 million light-years from end to end. 23 million light-years, more than 230 Milky Way diameters. A structure produced by one black hole. A single point in space, a singularity of collapsed matter, has reached across a volume of the universe larger than the distance between major galaxy clusters and actively filled that volume with energy. To put this in context, the distance from the Milky Way to the Andromeda Galaxy, our nearest major galactic neighbor, an approach we have known about for decades, a distance that will eventually result in a slow-motion merger of the two galaxies, is approximately 2.5 million light-years. Porphyrion's jets are nearly 10 times longer than that distance. If Porphyrion were centered on the Milky Way, one of its jet lobes would extend past Andromeda, past the Triangulum Galaxy, past the entire local group, and deep into the space between galaxy clusters, territory that belongs to no galaxy at all. The host galaxy of Porphyrion sits roughly 7.5 billion light-years away, which means we are seeing it as it was when the universe was roughly half its current age. At that time, a period of intense cosmic activity when supermassive black holes across the universe were feeding at extraordinary rates, something aligned in Porphyrion's environment to allow its jets to grow without interruption for what may have been hundreds of millions of years. The physics required to sustain this are extraordinary. The jet must remain magnetically coherent across 23 million light-years. The plasma it carries must retain enough energy to keep the terminal lobes radiating at radio frequencies bright enough for us to detect, billions of light-years away, with instruments on Earth. The black hole at the center must have sustained its feeding phase long enough for the jet to travel that distance, and at the speed of light, even light itself would require over 23 million years to make that journey. The jet has been underway, uninterrupted, for longer than that. But the most cosmologically significant aspect of Porphyrion is not its size alone, it is where its lobes terminate. At 23 million light-years in extent, Porphyrion's jet lobes do not end in empty, featureless intergalactic space. They end in regions where the large-scale structure of the universe, the cosmic web of filaments and voids that organizes all matter on the grandest scales, begins to impose itself on the intergalactic medium. The lobes are not just floating in space, they are interacting with that structure. They are injecting energy, magnetic fields, and turbulence into regions of the universe that are themselves part of the scaffolding on which galaxy clusters form and evolve. This is a feedback mechanism at a scale that was not previously considered possible for a single object. When astronomers talk about feedback, the way black holes influence their environments, they usually mean feedback on the scale of a single galaxy or a galaxy cluster. A black hole heats the gas around it, preventing it from cooling and collapsing into new stars. This is well established, but Porphyrion appears to be operating feedback on a scale that spans the distance between clusters. A single black hole actively reshaping the thermodynamic environment of the cosmic web itself. The implications of this are still being worked through. If Porphyrion is not an isolated anomaly but an extreme example of a process that is more common than previously assumed, then the history of how the large-scale structure of the universe formed may need to be rewritten in places. The energy injected by the largest giant radio galaxies could have influenced the formation of structures far beyond the galaxies that produced them, seeding turbulence in cosmic filaments, altering the temperature of the intergalactic medium across tens of millions of light-years, potentially affecting where and how new galaxies eventually form. This is the strange and vertiginous place where the science of giant radio galaxies currently sits, not in the comfortable territory of established textbooks, but at the frontier where every new observation seems to complicate the picture rather than simplify it. And it raises a question that has no comfortable answer yet. How do we define the size of a galaxy like Porphyrion? Its host galaxy, in terms of stars, might be relatively modest. If you measured it the way you measure IC 1101, by stellar mass, by luminous radius, by the distribution of ancient light, it would not break any records. But the structure that black hole has created, the physical footprint it has stamped on the universe, covers 23 million light-years of space. Is that the galaxy's size? Or is it something else, something for which astronomy does not yet have a fully satisfying name? This is exactly the kind of question that makes cosmology what it is, not a discipline of settled answers, but one of continuously shifting thresholds. Every definition holds until something forces it to expand. IC 1101 is the largest galaxy by stellar mass and luminous extent. Alcyonius held the record by physical footprint until Porphyrion, and Porphyrion is now the largest known structure produced by a single galaxy, by a single black hole in the observable universe. Whether something larger is still waiting to be found in the data we have not yet fully processed is, quite simply, unknown. What is known is that these objects exist at the intersection of two of the universe's most extreme phenomena, the most massive black holes ever to form, and the large-scale architecture of the cosmos itself. They are not separate from the cosmic web. They are in dialogue with it, pouring energy into it across distances that make the gap between neighboring galaxies look like an afterthought. Which brings us to the web itself. Because to truly understand why Alcyonius could grow to 16 million light-years, and why Porphyrion could reach 23, and why IC 1101 became what it is, you have to understand the structure that surrounds all of them. The invisible framework of dark matter and gas and gravitational attraction that organizes the entire universe into something that looks, at large enough scales, less like a random scattering of light and more like something almost biological. A network of filaments and voids so vast that individual galaxies, even the giants, are just nodes within it. That is where we are going next. So we have been standing close to these giants, close enough to trace the architecture of their jets, to measure the spin of their black holes, to argue about where exactly a galaxy ends and empty space begins. But perhaps we have been standing too close. Because to understand what these structures truly are, what IC 1101 and Alcyonius and Porphyrion really mean, We need to step back, much further back, further than feels comfortable, further than the mind wants to go. Imagine you are looking at a painting, your nose almost touching the canvas. You can see individual brushstrokes, the texture of the paint, the precise color of a single pigment, but you cannot see the painting. You need to walk back across the room. And then, if the painting is large enough, back across the street. And then, if it is large enough, out of the city altogether. The universe is that kind of painting. When astronomers in the 20th century began charting the positions of thousands and then millions and then hundreds of millions of galaxies across the sky, something unexpected began to emerge. The galaxies were not scattered randomly like seeds thrown from a hand into the wind. They were not even distributed in the vaguely clumped patterns one might naively expect from a universe where gravity pulls matter together. Instead, the universe revealed something stranger and more intricate than anyone had imagined. Something that looked, at the largest scales, almost alive. The structure is called the cosmic web, and once you see it, you cannot unsee it. Picture a vast three-dimensional network stretching across the entire observable universe. Long, thread-like filaments of galaxies stretch across hundreds of millions of light-years, billions of stars strung like beads along invisible wires. Where filaments meet and intersect, matter piles up into enormous galaxy clusters, the densest nodes of the web, where hundreds or even thousands of galaxies crowd together in a gravitational knot. Between the filaments lie flat, sheet-like walls of galaxies, thinner structures connecting the denser threads, and between all of these, the filaments, the walls, the clusters, lie vast, dark, nearly empty expanses, the voids, the places where almost nothing lives. The cosmic web is not a metaphor. It is the actual, measurable architecture of reality across the largest scales we can probe. And it did not appear by accident. Cast your mind back to the earliest moments of the universe. Not to the Big Bang itself, but to the fraction of a second after it, when the universe was a nearly uniform sea of energy and matter in almost perfect equilibrium. Almost, but not quite. Quantum mechanics, the strange probabilistic physics that governs the smallest scales of reality, ensures that nothing can ever be perfectly uniform. Even in those first instants there were fluctuations, infinitesimal ripples in the density of matter and energy, deviations so small they would be invisible to any conceivable instrument of that era. But the universe had time. It had 13.8 billion years. Gravity is a patient sculptor. Those infinitesimal overdensities attracted slightly more matter than the regions around them. The slightly denser regions became denser still, while the regions around them became correspondingly emptier, their matter bleeding away toward the gravitational pull of their neighbors. Dark matter, that invisible, abundant, gravitationally active substance we still do not fully understand, fell into these overdense regions first, forming the scaffolding. Ordinary matter followed, collecting along the paths laid down by dark matter halos. Over hundreds of millions, then billions of years, the nearly featureless early universe gradually organized itself into the elaborate lacework we see today. The cosmic web is, in a very literal sense, a fossil record of quantum uncertainty. Every filament, every void, every massive galaxy cluster traces its origin back to a quantum fluctuation so small it had no individual existence, only a statistical probability. The universe we inhabit is the amplified echo of randomness at the smallest possible scale. This is worth pausing on, because it is genuinely astonishing. The largest structures in existence, structures spanning hundreds of millions of light-years, are the direct descendants of fluctuations so tiny They existed only as probabilities in the moments after the Big Bang. The cosmic web is what happens when quantum physics meets 13.8 billion years of gravity. Now, within this web, the filaments and walls and clusters are not all the same. Some regions of the cosmic web are more extreme than others, and in the last few decades, astronomers have mapped structures so large they have begun to make cosmologists uncomfortable. The Sloan Great Wall, discovered in 2003 using data from the Sloan Digital Sky Survey, stretches roughly 1.4 billion light-years across the sky. It is a vast sheet of galaxies, a cosmic membrane connecting clusters and filaments into a single coherent structure. When it was found, it was the largest known structure in the universe. It held the title for less than a decade. The Hercules Corona Borealis Great Wall, identified in 2013 and refined in subsequent years, is estimated to span somewhere between 6 and 10 billion light-years. To put that in perspective, the observable universe, everything we can possibly see from Earth, the entire volume of space from which light has had time to reach us in 13.8 billion years, is approximately 93 billion light-years across. The Hercules Corona Borealis Great Wall is a single coherent structure stretching a substantial fraction of the distance across everything we can observe. Structures like these create a genuine tension with one of cosmology's foundational assumptions. The cosmological principle holds that, at sufficiently large scales, the universe should look the same in every direction. It should be homogeneous and isotropic, a smooth sea of matter with no preferred locations or directions. The cosmic web is expected, and is in fact consistent with the cosmological principle at the scales where it becomes a foam-like network, with no single filament or cluster large enough to dominate the overall picture. But structures like the Hercules Corona Borealis Great Wall push against that expectation. At the scale they exist, the universe is supposed to have already averaged out into uniformity. The existence of such enormous coherent structures has not disproven the cosmological principle, but it has forced cosmologists to reckon with the question of how large is large enough. The universe may be telling us that our models of its large-scale behavior, while remarkably successful, are not yet complete. And then there is the giant arc, discovered in 2021 by astronomer Alexia Lopez. Spanning approximately 3.3 billion light-years, it appears to be a vast crescent of galaxies, galaxy clusters, and gas, its geometry so regular and its scale so enormous that it immediately invited debate about whether it was a real coherent structure or a projection effect. The conversation continues, but it is another data point in a growing collection of observations suggesting that the universe organizes itself into structures somewhat larger and somewhat more dramatic than our tidiest theoretical models predicted. All of this sets the stage for understanding the voids. The cosmic web's filaments and walls get most of the attention because that is where the galaxies are, and galaxies are bright. But the voids, the dark spaces between the threads, are in many ways the more fundamental feature of the web's architecture. If you were to take the entire observable universe and divide it by volume, the voids would win, and it would not be close. Cosmic voids make up roughly 80% of the universe's total volume. The web of filaments, walls and clusters that contains almost all the matter and light we can observe is threaded through a much larger emptiness, like a delicate lace curtain that is mostly holes. Individual cosmic voids range enormously in size. The smaller ones span perhaps 30 to 50 million light-years across. The larger ones, sometimes called supervoids, can exceed 300 million light-years in diameter. The Bhuta's void, one of the most famous, stretches approximately 250 million light-years across and contains almost nothing. In a region of space where you might expect to find thousands of galaxies, there are perhaps 60. Astronomers who first characterized the Boötes void in 1981 reportedly joked, with the dark humor of people confronting something genuinely unsettling, that if the Milky Way had been located at its center, we would not have known there were other galaxies until the 1960s. Mapping voids is not straightforward. Unlike a filament which lights up with the glow of a billion suns, a void is defined by what is not there. Astronomers identify voids by tracing the distribution of galaxies in three-dimensional surveys and finding the regions that galaxy surveys consistently skip over, the holes in the net. It is cartography of absence, and absence, it turns out, has structure. Voids are not simply passive emptiness. They have dynamics of their own. Because the density of matter inside a void is lower than the cosmic average, the gravity from surrounding filaments gently pulls matter out of voids over time, making them emptier still. Meanwhile, the relative underdensity within a void means that its interior expands slightly faster than the universe as a whole. Voids are, in a sense, inflating from the inside. This has measurable effects on light passing through them, effects that cosmologists can use to study the properties of dark energy and the rate of cosmic expansion. But voids are not entirely empty. The galaxies that do exist inside them are fascinating objects in their own right. Void galaxies tend to be smaller, bluer, and more actively star-forming than their counterparts in denser environments. Without the harassment of nearby neighbors, constant minor mergers, and the ram pressure stripping that affects galaxies in clusters, void galaxies evolve in relative isolation. They are quieter, in a sense, more innocent. They have experienced less violence than their cousins in the crowded filaments. This brings us to something that might seem counterintuitive at first, but which connects everything we have been exploring. Alcyonius and Porphyrion, those radio galaxies whose jets stretch across 5 and 23 million light-years respectively, do not live in the densest, most spectacular regions of the cosmic web. They do not anchor the most massive galaxy clusters or preside over the richest filaments. They tend to be found near voids, in underdense environments, at the quieter margins of the cosmic web, where the surrounding intergalactic medium is thin and its pressure is low. This is not a coincidence. It is physics. The jets that erupt from the central black holes of radio galaxies are extraordinarily powerful, but they are not infinitely robust. As they propagate outward from their source, they push against the intergalactic medium, the diffuse gas that permeates the space between galaxies. In a dense environment, that ambient gas pushes back hard. It disrupts the jets, bends them, strips away their coherence, and ultimately limits how far they can travel before dissolving into turbulence. The jets of radio galaxies in rich cluster environments are typically shorter, more distorted, and more chaotic than those in emptier surroundings. But near a void, where the intergalactic medium is thinner than anywhere else in the universe, where there is almost nothing to push back, the jets can propagate with remarkable freedom. The low ambient pressure of void-adjacent regions is precisely the environment in which a jet can maintain its coherence across truly extraordinary distances. Alcyonius grew to the size it did not just because of its black hole, not just because of the particular physics of its plasma jets, but because it happened to occupy a cosmic address where almost nothing stood in its way. The universe's emptiest places are, paradoxically, the stage for its most physically extreme individual objects. The largest things tend to grow in the quietest neighborhoods. There is something almost poetic about this. The cosmos rewards isolation with scale. Porphyrion pushes this further still. At 23 million light-years, with two jets that together span a distance larger than the gap between the Milky Way and some of its most distant satellite galaxies. Porphyrion exists in an environment so underdense that the jets encounter almost no resistance for millions of light years in any direction. Its scale is not despite the void. Its scale is because of the void. This relationship between emptiness and extremity reframes how we think about the cosmic web. The web is not just a map of where things are, it is an explanation of what things become. The environment written in large-scale structure shapes the individual objects within it, governing how they grow, how they die, and how large they can ultimately become. And now, having pulled back this far, having moved from the individual galaxy to the local group, to the cosmic web, to the supervoids and the great walls, let us take one final step back to take in the full picture. IC 1101, 100 trillion stars, a stellar halo stretching perhaps 4 million light-years in diameter, the largest galaxy we have yet identified by stellar mass and optical extent. A structure so large that if our entire local group of galaxies, the Milky Way, Andromeda, and their dozens of smaller companions, were placed inside it, they would fit with room to spare. A structure we have spent 2 chapters trying to fully comprehend. From the scale of the cosmic web, IC 1101 is a bright knot in a filament, not a metaphor, not an approximation, a literal description of its position and relative scale within the larger architecture. IC 1101 sits at the heart of the galaxy cluster Abell 2029, which is itself one node in a larger supercluster structure. That supercluster is one concentration among many within a broader filament of the cosmic web, and that filament is one thread among countless others in a structure so vast that astronomers have not yet agreed on where it ends, or whether the concept of its ending is even meaningful. IC 1101's 4 million light-year halo is staggering from the inside. From the outside, from the perspective of the cosmic web, it is a bright point, a period at the end of a sentence, a single pixel in an image so large no screen could ever render it. This is not diminishment, or rather, it is diminishment in the truest sense of the word, a reduction that reveals rather than obscures. To see IC 1101 as a knot in a filament is not to make it smaller, it is to understand what kind of thing it is. It is a concentration of matter at a crossroads of the web, a place where the slow accumulation of billions of years of mergers and gravitational harvesting has produced a single brilliant node. It is punctuation in a sentence we are only beginning to read. And what happens to punctuation? What happens to the nodes? What happens to IC 1101 as the universe continues to age, as the cosmic web continues to evolve, as the voids grow emptier and the filaments stretch thinner across an expanding space? We have been exploring what these giants are, and how they came to be, and where they live. But the universe does not hold still. The structures we have been studying are not frozen monuments. They are part of a story that is still being written. And the next chapter of that story, the fate of the giants, is one of the strangest, and in some ways most unsettling, that cosmology has to tell. The fate of giants, what becomes of the universe's largest structures, we have been pulling back, further and further. From our solar system to our galaxy, from our galaxy to its nearest neighbors, from clusters to superclusters to the vast filaments and voids of the cosmic web. And somewhere in that process of stepping back, of trading intimacy for perspective, something shifts. The structures stop feeling like places and start feeling like patterns. The universe stops looking like a collection of things and starts looking like a single, breathing architecture, ancient, intricate, and indifferent to whether anyone is watching. But we have been watching, and having watched, having traced the threads of the cosmic web from their origins in quantum whispers to their present grandeur, there is one question left, the question we have been circling without quite naming. Not where did all of this come from? Not how large can a single structure grow, but what happens next? What becomes of the giants when the universe itself has plans of its own? The answer is not a comfortable one, but it is, in its own way, magnificent. Begin with IC 1101, the Colossus. The galaxy that has anchored this entire journey, that soft elliptical glow sitting more than 1 billion light-years away, assembled over billions of years through the patient accumulation of hundreds of smaller galaxies. Even now, as you consider it, it continues to grow. Minor mergers are still occurring at its fringes. Small satellite galaxies, drawn in by gravity's inexorable pull, are spiraling inward and being absorbed into the diffuse outer halo, adding their stellar mass to an already incomprehensible total. In this sense, IC 1101 is not finished. It is still technically in the process of becoming, but look more carefully and you begin to see the signs of something else, something quieter. IC 1101 is an elliptical galaxy, and one of the defining characteristics of elliptical galaxies is that they have largely exhausted their supply of cold gas. Cold gas is the raw material of star formation. It is the stuff that collapses under its own gravity, heats up, ignites, and becomes a new sun. In spiral galaxies like the Milky Way, cold gas still pools in the disk, still feeds new generations of stars, still lights the arms with the blue-white blaze of young stellar fire. In IC 1101, that process has slowed to something close to stillness. The galaxy is not dead, but it is aging. The stars being born inside it now are rare exceptions rather than the rule, and the dominant stellar population consists of older, redder, cooler stars, the long-lived embers of a fire that burned most fiercely billions of years ago. This is what astronomers call a red and dead galaxy. The phrase sounds brutal, but it captures something real. The grand creative phase of IC 1101's life is behind it. What remains is a long, slow twilight, an immense structure still gathering occasional mass at its edges, but internally quieting, its light growing redder and dimmer with each passing billion years as its older stars age off the main sequence and its younger stars grow fewer. And yet even this twilight will not last forever, because the universe itself is changing in ways that will eventually overtake even the largest structures we know. For the past several billion years, the expansion of the universe has been accelerating, not slowing down as you might expect from a universe full of matter pulling gravitationally on itself, but speeding up, driven by something we call dark energy, a property of space itself that generates a repulsive effect at the largest scales. Dark energy does not act locally. It does not tear apart galaxies or solar systems or even galaxy clusters bound tightly enough by gravity. But at the scale of the cosmic web, at the scale of the most loosely associated filaments and walls, it is already winning. The most remote regions of the cosmic web, those vast sheets of galaxies and the delicate bridges between clusters, are already being stretched. Over billions of years, the expansion will overwhelm the gravitational threads that connect distant structures, severing the loosest associations first, then gradually pulling apart even modestly connected regions. New galaxy clusters will cease to form. The raw material that would have gathered into the next generation of large-scale structures is already being dispersed faster than gravity can collect it. The cosmic web, that extraordinary fossil record of the universe's earliest moments, is not permanent. It is a phase, and the universe is slowly, inexorably moving on to the next one. For IC 1101, this means isolation. The galaxy already sits at the center of a massive cluster, surrounded by hundreds of smaller galaxies within its gravitational reach. For a time, for hundreds of billions of years, this local neighborhood will remain intact. Gravity is strong enough, at these scales, to hold the cluster together even as the universe outside expands. But the larger supercluster structures beyond, the faint filamentary connections to other clusters, the distant galaxies that are now merely very far away, these will recede, faster and faster, until, eventually, they pass beyond what physicists call the cosmic horizon, the boundary beyond which the expansion of space carries objects away faster than light can travel. Once something crosses that threshold, it does not merely become difficult to observe. It becomes permanently, irrevocably unreachable. The light it emits will never arrive. It ceases to exist, in any practical sense, within our universe. IC 1101's observable universe will shrink, not because the galaxy itself is moving, but because the space between it and everything else is growing. Over trillions of years, the view from inside IC 1101, if anything were there to look, would simplify. Distant galaxies would redshift toward invisibility, the cosmic background radiation would cool to nearly nothing, and eventually the only light in the sky would come from within the local cluster itself, a gravitationally bound island in an expanding sea with no visible shore. Now consider the giant radio galaxies, Alcyoneus and Porphyrion, those extraordinary structures whose jets extend for tens of millions of light-years across intergalactic space. They too have a trajectory, and it bends towards silence. The jets that define these galaxies are powered by accretion, by matter falling into the supermassive black holes at their centers and releasing enormous energy in the process. But accretion is not infinite. The supply of infalling material fluctuates with the availability of gas and the merger history of the host galaxy. At some point, as the local environment becomes depleted and the galaxy's gas reserves diminish, the accretion rate will decline. The jets will weaken. They will lose the internal energy needed to maintain their extraordinary coherence across millions of light-years. They will begin to fray. What is left behind when a jet fades is something called a radio lobe. This is the diffuse, expanded cloud of magnetized plasma that the jet has been inflating over millions or tens of millions of years, an enormous bubble of energetic particles, dimly glowing in radio wavelengths, drifting in intergalactic space like smoke after the fire has gone out. For a while, these lobes remain detectable. Radio telescopes can pick up their fading emissions, but they are no longer being fed. They are coasting on stored energy, and that energy dissipates, slowly but surely, carried away by the expansion of the plasma, radiated away as radio waves that travel outward and are absorbed by nothing in particular. Over hundreds of millions of years, the lobes thin. Their radio signature drops below the threshold of detectability. The plasma disperses into the surrounding intergalactic medium, contributing its small thermal energy to the vast warmth of cosmic space. And what remains of Alcyoneus and Porphyrion, those staggering structures that once extended further than most galaxies have ever traveled, is nothing but the quiet host galaxy at the center and perhaps a whisper of slightly warmer gas in the intergalactic void. Enormous structures, slowly dissolving back into the silence from which they briefly emerged. This is not tragedy, it is physics. But physics, observed at sufficient scale, has its own kind of elegy. Let us go further into the future than any human civilization has existed, further than the Earth has been alive, further even than the current age of the universe would seem to suggest is meaningful to consider. Because the fate of IC 1101, of all galaxies, continues beyond the exhaustion of their jets and the isolation of their clusters. It continues until the very last star goes dark. The longest-lived stars in the universe are red dwarfs. Small, cool, miserly with their hydrogen fuel, they burn at a fraction of the intensity of stars, like our Sun. But they burn for an incomparably longer time. Where the Sun has a lifespan of roughly 10 billion years, a red dwarf of the smallest variety may burn steadily for 10 trillion years. That is 1,000 times longer than the current age of the universe. And in the far future of IC 1101, these red dwarfs will be the last lights on. Everything else, the sun-like stars, the massive blue giants, the stellar remnants that orbit one another in binary systems, will have long since burned out, collapsed into white dwarfs or neutron stars or black holes. Only the red dwarfs will still be fusing hydrogen, still generating light, still technically maintaining something we might call stellar life. And then, one by one, they too will exhaust their fuel. Not in explosion. Red dwarfs do not go supernova. They simply cool. They fade from red to infrared to nothing. The last one will go dark, and when it does, IC 1101, the largest galaxy in the observable universe, assembled over billions of years from the wreckage of hundreds of smaller galaxies, home to 100 trillion stars at its peak, will be a galaxy of ghosts. White dwarfs slowly cooling toward black, neutron stars spinning down, and at the center the supermassive black hole, still there, still enormous, still technically the most gravitationally dominant object in the region. But even black holes do not last forever. Stephen Hawking demonstrated theoretically that black holes emit radiation, an extraordinarily slow quantum process by which pairs of virtual particles form at the event horizon, one falling in and one escaping, gradually carrying mass energy away from the black hole over time. The process is so slow that for the black holes we know today, the radiation is utterly negligible, swamped by the background temperature of the universe, lost in the noise. But in the far future, in a cold and empty cosmos where the background temperature has dropped to nearly absolute zero, Hawking radiation will eventually dominate. Black holes will evaporate. Slowly, then more rapidly as they shrink and the radiation intensifies in a feedback loop. The timescale for this is staggering. For a stellar mass black hole, evaporation takes roughly 10 to the 67th years. For the supermassive black hole at the center of IC 1101, billions of times more massive, the timescale extends to something in the range of 10 to the 100th years, a number so large it has no useful analogy. The current age of the universe is roughly 14 billion years, which is approximately 10 to the 10th. The evaporation of IC 1101's central black hole will require a time span longer by a factor with 90 more zeros on it than the current age of the universe, and when it is gone, there is nothing. Not darkness in the way we mean it, not a room with the lights off, a genuine structural nothing, no photons, no matter, no signal, space continuing to expand, carrying its emptiness outward, with no structure left to interrupt it. This is the final chapter of IC 1101. The colossus, the accumulation of 100 trillion stars, the largest known galaxy in the observable universe, will end in complete and absolute silence, not with a bang, not even with a whimper. Just the last quantum of Hawking radiation departing from an evaporating singularity, and then expansion and quiet forever. And yet, here we are, right now, in this specific moment in cosmic history, a moment that is by the standards of the universe's full timeline, extraordinarily early. The universe is 14 billion years old, but it will persist, in various stages of structural decay, for timescales that make 14 billion years look like the first breath of a sentence that takes 10 to the 100th years to finish. We are at the beginning. The cosmic web is still intact. Stars are still forming. Galaxies are still merging. IC 1101 is still growing. The giants are still here, and they are here to be seen, and they are being seen by us from here. From this pale blue dot, as someone once called it, orbiting an unremarkable middle-aged star in a spiral galaxy of perhaps 400 billion stars, itself a modest participant in a local group, itself a minor node in the filamentary structure of the larger universe. We are, by any cosmological measure, deeply ordinary. Our location is not special, our star is not extraordinary, our galaxy is not the largest, not the most luminous, not the most structurally significant object in the cosmic web. And yet, something happened here that did not happen in IC 1101. Something happened in this ordinary spiral galaxy, on this ordinary rocky planet, that as far as we know has not happened anywhere else we have yet found. Consciousness arose, not the passive existence of matter and energy, not the slow burning of stars or the long spiral of merging galaxies, but something that knows it exists, something that looks up, something that asks questions about the darkness and then builds instruments to answer them. Something that discovered IC 1101, that measured its light, that calculated its size, that traced the cosmic web back to its quantum origins and forward to its final dissolution. Think about what that actually means. The light that left IC 1101 more than 1 billion years ago, when Earth held nothing more complex than single-celled life in its shallow seas, arrived at telescopes built by beings who descended from those very cells. Beings who measured that ancient light, ran the numbers, and determined that they were looking at a structure roughly 6 million light-years across, assembled from the wreckage of hundreds of galaxies over billions of years, burning with 100 trillion suns. They held that knowledge in minds that weigh about 3 pounds and run on roughly 20 watts of metabolic power. There is something in that asymmetry worth sitting with. Not comfort exactly, not the reassurance that we matter in some cosmological accounting. The universe is not arranging itself around us, and the fate of IC 1101 will proceed entirely without our input. But meaning perhaps of a different kind, the kind that comes not from being central, but from being capable of comprehension. The universe has, in at least one small corner of one modest spiral galaxy, developed the capacity to contemplate itself, to look outward across 1 billion light-years and say, there is something there, and it is larger than anything we have words for, and it will be gone someday, and we understand why. That is not nothing. In a universe trending toward nothing, over time scales that dwarf all the structures we have spent this journey exploring, the existence of anything that comprehends its own impermanence is, at minimum, remarkable. At maximum, it might be the most remarkable thing that has happened since the Big Bang. The giants will fade, the jets will go quiet, the stars will burn out one by one, the last red dwarf cooling silently in the emptiness, the black holes evaporating over timescales the universe itself cannot remember. The cosmic web will unravel, the filaments will thin, the voids will grow until they are all there is. But right now, for this brief, extraordinary moment in the long life of the universe, the web is intact, the giants are burning, and we are here looking at them, measuring them, wondering about them, finding them beautiful. That is the thing about scale. Push it far enough in any direction, large enough, distant enough, old enough, and you expect to feel small. And you do, of course you do. How could you not, standing in the shadow of a galaxy 6 million light-years wide, assembled over billions of years, burning with 100 trillion suns? But push a little further, past the smallness, past the vertigo, and something else is waiting on the other side. Something that looks, if you let it, surprisingly like wonder. The largest galaxy in the observable universe is out there, and you know it is. And that, in the end, may be the most astonishing fact of all. We began with a single question buried inside a night sky. What are those lights? And in chasing that question, we crossed 100,000 light years just to reach the edge of home. Then we crossed a billion more. IC 1101 sits out there right now, aging in silence, a vast elliptical colossus, red and dimming, still pulling smaller worlds into its gravity with the patience of something that has never needed to hurry. The light we see from it left before complex life had written a single sentence on this planet. And yet here we are, reading that ancient signal, translating its meaning with instruments made of silicon and ambition. What this journey has quietly revealed is something stranger than any single measurement. The universe does not organize itself for human comprehension. It does not offer clean edges, settled definitions, or final answers. Galaxies blur into halos. Halos blur into filaments. Filaments stretch toward voids so enormous that emptiness itself becomes a kind of architecture. Even the word largest, the word we used to begin, turned out to be a negotiation, not a fact. And dark energy is still working. Quietly, invisibly, it stretches the threads of the cosmic web further apart with every passing second, pulling the universe toward a loneliness so complete it has no name yet. But here is what endures in all of this. Somewhere on a rocky world orbiting an ordinary star, inside an unremarkable galaxy among hundreds of billions of galaxies, a creature looked up. Not because it had to, because it wanted to know. IC 1101 will outlast everything we have ever built or imagined. But it will never do what you just did. It will never wonder what it is. And in all this vastness, that might be the most extraordinary thing the universe has ever produced.